Okay, our topic, Introduction to Infinite Series. So let's recall that so far we've focused on sequences. And a sequence is nothing more than an ordered list. So A1 is the first term, A2 is the second term, A3 is the third term, so on and so forth. Now, when we introduce the idea of an infinite series, essentially what you do is take that list and replace the commas with plus signs. So an infinite series is a sum of terms from a sequence. So you have this list of terms and you're adding them all together, and that's what your series is. So as an example, and we'll work through this in a couple different lectures, but 1 over 2 to the n. Sum n goes from 1 to infinity. So down here we have the first value for the index n, and then we go all the way to infinity. So when n equals 1, we get 1 over 2 to the 1, or a half. When n is 2, we get 1 over 2 squared, or a fourth, 1 over 2 cubed, 1 over 2 to the fourth, 1 over 2 to the fifth. Now, one way we can think about this is say, well, what does it mean to add up infinitely many terms? Well, the first thing we can do to try and answer that question is say, well, we don't know what it means to add up infinitely many terms, but we know how to add up finitely many terms. So say the first two. We would call that S2. Or the first three, S3. Or the first four, which would be S4. And that all comes from this definition here, the Kth partial sum. So the Kth partial sum of our infinite series is the sum of the first k terms. And there's kind of a key typo there. Instead of infinity, we're summing to k. So we don't know what it means to add all the terms in the series, so we just stop at k. So a1, a2 up to ak. And here were our examples. This is the second partial sum, a half plus a fourth. Third partial sum, a half plus a fourth plus an eighth. And we're going to dig a little bit more deeply into that, but this is the key tool to help us understand what it means to add up infinitely many terms in a series. The big question will be, and for now, we're going to assume for this entire lecture that our terms in the series are always greater than or equal to 0. So we assume that all a sub n, for now, are greater than or equal to 0. So what does it mean to add up infinitely many terms? And this, we're very comfortable adding finitely many terms, so we can use this construct to help answer this question. What does it mean to add up infinitely many terms, and does this actually sum to something finite? So let's delve into the partial sum a bit for this example. The partial sums. So we said the first partial sum, that was just 1/2. The second partial sum is the sum of these two. So we have 1/2 plus 1/4. And if we make columns here, we'll have one more column. Our third partial sum, a half plus a fourth plus an eighth. And why don't we write these in decimals? This third partial sum would be 0.875. The second partial sum is 0.75, and of course the first partial sum is 0.5. So those are our first three partial sums. Let's go a little bit further. So our fourth partial sum of these four terms, so a half plus a fourth plus an eighth plus a 16th, that is 0.9375. And if we go one further, our fifth partial sum, so you get the idea, all these terms, but then we add 1 over 32, that is 0.96875. And if we were to do the sixth partial sum, that would be 0.984375. So, looking at these partial sums will be the key to understanding what it means for a series to converge. Think about what it means as you increase k. As you increase k, you pick up more and more terms. Second partial sum has 2 terms. The third partial sum has 3 terms. The fourth partial sum has 4 terms. So the further you go down this list of partial sums, the more and more of these terms you're gobbling up. So, along those lines, as we move down this list, there's a key word there for this. As we move down this list, these numbers are representing partial sums that have more and more terms from the series. So as we go down this list, we're getting more and more terms from the series, which means if the thing converges, if the series converges, as we go down this list, we should be getting closer and closer to whatever that value is for the sum of the entire series. And that's the key. The key is to look at this as a sequence. So the sequence of Kth partial sums. And that will give us our definition of convergence for this series. If the limit of the sequence of Kth partial sums converges, that limit will be equal to the sum of these numbers here, all of the numbers. That limit of the Kth partial sums as a sequence will be equal to the series. So again, as you go down this list, if the series is converging, if this sum of all the infinite terms is in fact finite, as you go down this list, you should be getting closer and closer to that value. Because as you go down this list, you're adding more and more terms from the series. And that leads us to our definition here for series convergence. So our series, sum from n equals 1 to infinity of a sub n, converges to the value s if the limit as k goes to infinity of sk equals s. So the sum of the series s is equal to the limit of the partial sums. If the limit doesn't exist, we say the series diverges. So it's important to recognize right now, to take a pause and note that the definition for convergence of a series involves convergence of a sequence. So this is a good point to sit back and review the information about sequences and convergence of sequences, because you really want to make sure that you understand what it means for a sequence to converge as we now move into the idea of a series converging. And again, it all comes down to this idea of, as you move down the list of Kth partial sums, if the series in fact converges, as you move down that list, you should be honing in on that value of that series. what the actual sum of infinitely many terms is equal to. So this is the idea. You can also visualize this a little bit by relating it to improper integrals. So let's think back to our lecture on improper integrals and remember, so we'll say it's analogous to improper integrals. So remember, for improper integrals, we started with something like this. The integral, we'll say from 1 to infinity, of f of x dx. And we weren't really sure at first how to make sense of it, but then we said, we can break this up into two different things. The first step was, instead of integrating all the way to infinity, we stopped at t. And that was a problem that we knew from Calc 2, from our study of integral calculus. And then we noted that we could then send t on its way. So the picture for this, you had your f of x, and we were interested in this area below the curve f of x, so a non-negative function f of x on the interval 1 infinity. And the way we break it up to stay consistent with our colors here is we said, all right, let's stop at t and compute that area. That was this integral here. Then when we were finished, we sent t to infinity. And that turned the blue area into the black area. What we're doing now is very similar. What we're doing now is trying to make sense of the sum from n equals 1 to infinity of a sub n. That's a sum of infinitely many terms. And like we did in this case, we say, all right, you know what? We don't really know what it means to add up infinitely many terms, but we know how to stop at k. So we have this finite sum of k terms. Once we have that sum, we then send k on its way. So it's a very similar idea to what we did with improper integrals. We break down the process into two steps. One, we have a finite sum. We know how to deal with that. Then, once we finish that, we have some expression that will involve k. Then you let k go to infinity, and that's a limit problem, a calculus limit problem. So this is what it means for a series to converge. This is what it means for a sum of infinitely many terms to converge or to be finite, if this expression here is finite. If it's not, we say it diverges. So one natural thing to do here is to use an example to kind of sink our teeth into things and see how this works. And this is an example called a telescoping series, and we will see why that terminology is used momentarily. So in order to deal with this series, we have to actually go back to a technique from integral calculus to see, or to set up for it. We're going to rewrite this as one, factor out an n in the denominator. And in integral calculus, we learn a technique. It's really an algebraic technique that we learn to do integration, but we learn a technique called partial fractions. So this is something worth reviewing from your integral calculus work. But what partial fractions does is it tells us that we can rewrite this summand as the sum of two fractions, a over n plus b over n plus 1. For some a and some b, we don't know what they are yet, but we can solve for them. So in order to solve for a and b, we set things up in the following way. So let's focus on setting what's in the square brackets here equal to this summand here. So we have 1 over n times n plus 1 equals a over n plus b over n plus 1. And for the types of partial fractions problems that we'll deal with in this course, this approach will always work. So the first thing we do is multiply both sides by the original denominator here. So we multiply both sides by n times n plus 1. When we do that, on the left side, this n and n plus 1 will cancel with this n and this n plus 1. We're just left with 1. On the right-hand side, the n will cancel here. So we will have an a times n plus 1. And then the n plus 1 will cancel here, and we'll have bn. So this has gotten rid of all the division. Now the next step is to group by powers of n. So we rewrite this right-hand side as an plus a plus bn, and then we see we have these terms for n to the first, and then the others for n to the 0. So we rewrite this as 1 equals a plus b times n plus a. And we can now use this to solve for the coefficients. And the idea is we match up coefficients according to powers of n. So think on the left-hand side as this being 0 times n plus 1. What we now can do is match up these coefficients by saying the coefficient of n on the left has to match the coefficient of n on the right. The coefficient of 1, you can think of that as 1 times n to the 0 on the left, has to match that on the right. So in order for this equality to hold for all n, the idea is that you need these coefficients to match. So for instance, if there was an n squared term on the left and an n squared term on the right, you would match their coefficients as well. So this results in two equations, two unknowns. So the first, the blue equation here, will be a plus b equals 0, and then the green will be a equals 1. So we have two equations, two unknowns, and we see, well, a equals 1, and then we also see that this means that b equals minus 1. So this means that we can now plug a equals 1 here and b equals minus 1 here. And we now will have a new expression for our series. So this means, well, why don't we write it? 1 over quantity n times n plus 1 is a over n, which is 1 over n, plus b, right? That's minus 1 over n plus 1. So this is a new way to rewrite the summand in our series. Okay, so what do we do with this? That's kind of the natural question to ask now. So we have that the sum n equals 1 to infinity of 1 over n times n plus 1 equals the sum, n goes from 1 to infinity, of the quantity 1 over n minus 1 over n plus 1. And this is actually the only type of series that we're going to work with where we compute the value of the series. We compute the value that the series converges to directly from the definition of series convergence. So we go right to the Kth partial sum. So we compute the Kth partial sum, which, remember, we are calling Sk. So Sk is, remember, the definition is just take your series and instead of summing to infinity, you stop at k. So Sk is the sum n goes from 1 to k of 1 over n minus 1 over n plus 1. And we're actually going to flesh this out by writing the first several terms and the last several terms. So let's write this. The first term, I'll just put a label above it, is when n equals 1. So 1 over 1 minus 1 over 2. And when you do these, do not simplify. For instance, we could have just said that this is equal to a half, but you don't want to do that because you miss the pattern. What we're trying to get is the pattern. The second term, when n equals 2, we get 1/2 minus 1/3. For the third term, we get 1/3 minus 1/4. For the fourth term, we get 1/4 minus 1/5. And you may notice that there is a pattern here. And the pattern is that you see these pairings. The 1/5 will have a partner in the next term. And you see that the signs are opposite. So this one, negative 1/2, will cancel with the 1/2. The minus 1/3 will cancel with the third. The minus 1/4 will cancel with the 1/4. Minus 1/5 has a partner in the next term. So we see this partnering up in the beginning of the terms of the Kth partial sum. Now we do the end. So we do the last terms. So the last term, we'll write over here. So this is the case when n equals k. So when n equals k, that one's quick because you just take your summand and you just replace n with k. So that gives us 1 over k minus 1 over k plus 1. And you always want to run out a few terms at both beginning of the series and the end of the series to try and ID the pattern. So here now we do the k minus 1 term. And so come back and replace n with k minus 1. So we get 1 over k minus 1 minus 1 over k minus 1 plus 1, or 1 over k. We do the n equals k minus 2 term. So again, 1 over, just replace n with k minus 2. 1 over k minus 2 minus 1 over k minus 2 plus 1. So that's 1 over k minus 2 minus 1 over k minus 1. And then we have a bunch of preceding terms. And we can actually now make the same type of pairing. We see the 1 over k's here match. The 1 over k minus 1's match. 1 over k minus 2 has a partner in the previous term. And they have opposite signs, so they're all canceling. And looking at this now, we see that the only surviving terms are that 1 at the beginning and the minus 1 over k plus 1 at the end. So this whole thing equals 1 minus 1 over k plus 1. The reason this is called a telescoping series is you want to think of the old collapsible telescopes. So you have a bunch of right circular cylinders that get smaller in radii, and you collapse it. When you're not using it, you expand it when you're using it. This way of writing the Kth partial sum is the expanded telescope, and then this is the collapsed telescope. But remember, what is the Kth partial sum? The Kth partial sum, by definition, is the sum of the first k terms of the series. The bigger you make k, the closer you are getting to infinity in the index. More and more terms from the series you're adding up. And so as k gets bigger, your Kth partial sum should be approaching the value of the series. We now have an expression for that Kth partial sum. So we know now the sum of the first k terms is exactly 1 minus 1 over k plus 1. And by definition, the sum, n equals 1 to infinity, of our 1 over n times n plus 1 series is the limit as k goes to infinity of that Kth partial sum, which we just computed as 1 minus 1 over k plus 1. And that limit we can see is 1. So the way you can interpret that is the more and more terms you pile into the series, the larger k gets, the closer and closer that partial sum is getting to 1. And if you go all the way and add up all the terms in the series, infinitely many of them, you get exactly 1. And so we see that this series, the sum of this n equals 1 to infinity of this expression, when you add up all infinitely many terms, is exactly equal to 1. So it's an interesting example because, again, the telescoping series is the only series where you use directly the definition of convergence of a series as the limit of the sequence of Kth partial sums. That's the only time that we're going to directly use that definition to compute the sum of a series. We will get into much more in terms of series. We will look at many different ways to test series for convergence. But every one of those tests will always boil down to this definition of convergence of a series. This is what it means for a series to converge. We look at the limit of the Kth partial sums. And every test that we will work with throughout the rest of our coverage of infinite series, it all boils down to this. This is the engine driving everything, but we won't directly work with it except in the instance of the telescoping series.